Okay. Holy shit, what did I? It's supposed to be 23. Is it though? Who knows? Let's give it a look. Give it a look. Give it a look. Give it a, give it a, give it a, give it a.
When it comes time
gradient. And really what it does is it implements backpropagation. Now backpropagation is this algorithm that allows you to efficiently evaluate the gradient of some kind of a loss function with respect to the weights of a neural network. And what that allows us to do then is we can iteratively tune the weights of that neural network to minimize the loss function and therefore improve the accuracy of the network. So backpropagation would be at the mathematical core of any modern deep neural network library, like say PyTorch or JAX. So the functionality of micrograd is I think best illustrated by an example. So if we just scroll down here, you'll see that micrograd basically allows you to build out mathematical expressions. And here what we are doing is we have an expression that we're building out where you have two inputs, A and B. And you'll see that A and B are negative 4 and 2, but we are wrapping those values into this value object that we are going to build out as part of micrograd. So this value object will wrap the numbers themselves. And then we are going to build out a mathematical expression here where A and B are transformed into C, D, and eventually E, F, and G. And I'm showing some of the functionality of micrograd and the operations that it supports. So you can add two value objects, you can multiply them, you can raise them to a constant power, you can offset by 1, negate, squash at 0, square, divide by constant, divide by it, etc. And so we're building out an expression graph with these two inputs A and B, and we're creating an output value of G. And micrograd will, in the background, build out this entire mathematical expression. So it will, for example, know that C is also a value. C was a result of an addition operation, and the child nodes of C are A and B, because and it will maintain pointers to A and B value objects. So we'll basically know exactly how all of this is laid out. And then not only can we do what we call the forward pass, where we actually look at the value of G, of course, that's pretty straightforward. We will access that using the .data attribute. And so the output of the forward pass, the value of G, is 24.7, it turns out.
If I could only use GitHub. And first we have ML from scratch. This repo teaches you how ML actually works through practical implementation of algorithms like linear regression, decision trees, and support vector machines using Python. Following this repo will get you pretty comfortable with some Python libraries like NumPy and scikit-learn. Second is NN0 to Hero. This repo goes hand in hand with Andrej Karpathy's YouTube course, and it's just one of the best ways to truly understand neural networks. You'll build fundamental basics like backpropagation and activation functions, and eventually build a small neural network line by line. And third is 500 AI machine learning, deep learning, and computer vision.
out. But the big deal is that we can also take this G value object and we can call dot backward. And this will basically initialize backpropagation. At the node G. And what backpropagation is going to do is it's going to start at G and it's going to go backwards through that expression graph and it's going to recursively apply the chain rule from calculus. And what that allows us to do then is we're going to evaluate basically the derivative of G with respect to all the internal nodes like E, D, and C, but also with respect to the inputs A and B. And then we can actually query this derivative of G with respect to A. For example, that's A dot grad. In this case, it happens to be 138. And the derivative of G with respect to B, which also happens to be here, 645. And this derivative, we'll see soon, is very important information because it's telling us how A and B are affecting G through this mathematical expression. So in particular, A dot grad is 138. So if we slightly nudge A and make it slightly larger, 138 is telling us that G will grow, and the slope of that growth is going to be 138. And the slope of growth of B is going to be 645. So that's going to tell us about how G will respond if A and B get tweaked a tiny amount in a positive direction. Okay. Now, you might be confused about what this expression is that we built out here. And this expression, by the way, is completely meaningless. I just made it up. I'm just flexing about the kinds of operations that are supported by micrograd. What we actually really care about are neural networks. But it turns out that neural networks are just mathematical expressions, just like this one, but actually slightly bit less crazy even. Neural networks are just a mathematical expression. They take the input data as an input, and they take the weights of a neural network as an input, and it's a mathematical expression, and the output are your predictions of your neural net, or the loss function. We'll see this in a bit. But basically, neural networks just happen to be a certain class of mathematical expressions. But backpropagation is actually significantly more general. It doesn't actually care about neural networks at all. It only cares about arbitrary mathematical expressions, and then we happen to use that machinery for training of neural networks. Now, one more note I would like to make at this stage is that, as you see here, micrograd is a scalar-valued autograd engine. So it's working on the level of individual scalars, like -4 and 2. And we're taking neural nets and we're breaking them down all the way to these atoms of individual scalars and all the little pluses and times, and it's just excessive. And so obviously you would never be doing any of this in production. It's really just done for pedagogical reasons because it allows us to not have to deal with these n-dimensional tensors that you would use in modern deep neural network library. So this is really done so that you understand and refactor out backpropagation and chain rule and understanding of neural network training. And then if you actually want to train bigger networks, you have to be using these tensors, but none of the math changes. This is done purely for efficiency. We are basically taking all the scalar values, we're packaging them up into tensors, which are just arrays of these scalars. And then because we have these large arrays, we're making operations on those large arrays that allows us to take advantage of the parallelism in a computer. And all those operations can be done in parallel, and then the whole thing runs faster. But really, none of the math changes, and they're done purely for efficiency. So I don't think that it's pedagogically useful to be dealing with tensors from scratch. And that's why I fundamentally wrote micrograd, because you can understand how things work at the fundamental level, and then you can speed it up later. Okay, so here's the fun part. My claim is that micrograd is what you need to train neural networks, and everything else is just efficiency. So you'd think that micrograd would be a very complex piece of code, and that turns out to not be the case. So if we just go to micrograd, and you'll see that there's only 2 files here in micrograd. This is the actual engine. It doesn't know anything about neural nets, and this is the entire neural nets library on top of micrograd. So engine and nn.py. So the actual backpropagation autograd engine that gives you the power of neural networks is literally 100 lines of code of like very simple Python, which we'll understand by the end of this lecture. And then nn.py, this neural network library built on top of the autograd engine, is like a joke. It's like we have to define what is a neuron, and then we have to define what is a layer of neurons, and then we define what is a multi-layer perceptron, which is just a sequence of layers of neurons. And so it's just a total joke. So basically, there's a lot of power that comes from only 150 lines of code. And that's all you need to understand neural network training, and everything else is just efficiency. And of course, there's a lot to efficiency, but fundamentally that's all that's happening. Okay, so now let's dive right in and implement micrograd step by step. The first thing I'd like to do is I'd like to make sure that you have a very good understanding intuitively of what a derivative is and exactly what information it gives you. So let's start with some basic imports that I copy paste in every Jupyter notebook always. And let's define a function, a scalar valued function, f of x, as follows. So I just made this up randomly. I just wanted a scalar valued function that takes a single scalar x and returns a single scalar y. And we can call this function, of course, so we can pass in, say, 3.0 and get 20 back. Now, we can also plot this function to get a sense of its shape. You can tell from the mathematical expression that this is probably a parabola. It's quadratic. And so if we just create a set of scalar values that we can feed in using, for example, a range from -5 to 5 in steps of 0.25. So x is just from -5 to 5, not including 5, in steps of 0.25. And we can actually call this function on this NumPy array as well. So we get a set of y's if we call f on x's. And these y's are basically also applying the function on every one of these elements independently. And we can plot this using matplotlib. So plt.plot x's and y's, and we get a nice parabola. So previously here we fed in 3.0 somewhere here, and we received 20 back, which is here, the y-coordinate. So now I'd like to think through what is the derivative of this function at any single input point x. Right, so what is the derivative at different points x of this function? Now, if you remember back to your calculus class, you probably derived derivatives. So we take this mathematical expression, 3x squared minus 4x plus 5, and you would write out on a piece of paper and you would, apply the product rule and all the other rules and derive the mathematical expression of the great derivative of the original function. And then you could plug in different x's and see what the derivative is. We're not going to actually do that because no one in neural networks actually writes out the expression for the neural net. It would be a massive expression. It would be, thousands, tens of thousands of terms. No one actually derives the derivative, of course. And so we're not going to take this kind of like symbolic approach. Instead, what I'd like to do is I'd like to look at the definition of derivative and just make sure that we really understand what the derivative is measuring, what it's telling you about the function. And so if we just look up derivative, we see that, okay, so this is not a very good definition of derivative. This is a definition of what it means to be differentiable. But if you remember from your calculus, it is the limit as h goes to 0 of f of x plus h minus f of x over h. So basically what it's saying is if you slightly bump up, you're at some point x that you're interested in, or a, and if you slightly bump up, you slightly increase it by a small number h, how does the function respond? With what sensitivity does it respond? What is the slope at that point? Does the function go up or does it go down? And by how much? And that's the slope of that function, the slope of that response at that point. And so we can basically evaluate the derivative here numerically by taking a very small h. Of course, the definition would ask us to take h to 0. We're just going to pick a very small h, 0.001. And let's say we're interested in point 3.0. So we can look at f of x, of course, is 20. And now f of x plus h. So if we slightly nudge x in a positive direction, how is the function going to respond? And just looking at this, do you expect f of x plus h to be slightly greater than 20? Or do you expect it to be slightly lower than 20? And since this 3 is here, and this is 20, if we slightly go positively, the function will respond positively. So you'd expect this to be slightly greater than 20. And now by how much is telling you the strength of that slope, right? The size of that slope. So f of x plus h minus f of x, this is how much the function responded in the positive direction. And we have to normalize by the run, so we have the rise over run to get the slope. So this, of course, is just a numerical approximation of the slope because we have to make h very, very small to converge to the exact amount. Now, if I'm doing too many zeros, at some point, I'm going to get an incorrect answer because we're using floating point arithmetic and the representations of all these numbers in computer memory is finite, and at some point we get into trouble. So we can converge towards the right answer with this approach. But basically, at 3, the slope is 14. And you can see that by taking 3x squared minus 4x plus 5 and differentiating it in our head. So 3x squared would be 6x minus 4, and then we plug in x equals 3, so that's 18 minus 4 is 14, so this is correct. So that's at 3. Now how about the slope at, say, -3? What would you expect for the slope? Now, telling the exact value is really hard, but what is the sign of that slope? So at -3, if we slightly go in the positive direction at x, the function would actually go down. And so that tells you that the slope would be negative. So we'll get a slight number below 20. And so if we take the slope, we expect something negative 22. Okay. And at some point here, of course, the slope would be 0. Now for this specific function, I looked it up previously, and it's at point 2 over 3. So at roughly 2 over 3, that's somewhere here, this derivative will be 0. So basically at that precise point, at that precise point, if we nudge in a positive direction, the function doesn't respond. This stays the same almost. And so that's why the slope is 0. Okay, now let's look at a bit more complex case. So we're going to start, complexifying a bit. So now we have a function here with output variable b that is a function of 3 scalar inputs, a, b, and c. So a, b, and c are some specific values, 3 inputs into our expression graph, and a single output d. And so if we just print d, we get 4. And now what I'd like to do is I'd like to again look at the derivatives of d with respect to a, b, and c. And think through, again, just the intuition of what this derivative is telling us. So in order to evaluate this derivative, we're going to get a bit hacky here. We're going to again have a very small value of h. And then we're going to fix the inputs at some values that we're interested in. So this is the point ABC at which we're going to be evaluating the derivative of d with respect to all a, b, and c at that point. So there's the inputs, and now we have d1 is that expression. And then we're going to, for example, look at the derivative of d with respect to a. So we'll take a and we'll bump it by h, and then we'll get d2 to be the exact same function. And now we're going to print, f1, d1 is d1, d2 is d2, and print slope. So the derivative, or slope, here will be, of course, d2 minus d1 divided h. So d2 minus d1 is how much the function increased when we bumped the specific input that we're interested in by a tiny amount. And this is then normalized by h to get the slope. So, so if I just run this, we're going to print d1, which we know is 4. Now d2 will be bumped, a will be bumped by h. So let's just think through a little bit what d2 will be printed out here. In particular, d1 will be 4. Will d2 be a number slightly greater than 4 or slightly lower than 4? And it's going to tell us the sign of the derivative. So we're bumping a by h. B is minus 3, c is 10. So you can just intuitively think through this derivative and what it's doing. A will be slightly more positive, but b is a negative number. So if a is slightly more positive, because b is negative 3, we're actually going to be adding less to d. So you'd actually expect that the value of the function will go down. So let's just see this. Yeah, and so we went from 4 to 3.9996. And that tells you that the slope will be negative, and then will be a negative number because we went down. And then the exact number of slope will be, exact amount of slope is negative 3. And you can also convince yourself that negative 3 is the right answer mathematically and analytically, because if you have a times b plus c and you have calculus, then differentiating a times b plus c with respect to a gives you just b. And indeed, the value of b is negative 3, which is the derivative that we have. So you can tell that that's correct. So now if we do this with b, so if we bump b by a little bit in a positive direction, we'd get different slopes. So what is the influence of b on the output d? So if we bump b by a tiny amount in a positive direction, then because a is positive, we'll be adding more to d, right? So, and now what is the sensitivity? What is the slope of that addition? And it might not surprise you that this should be 2. And why is it 2? Because d of d by db, differentiating with respect to b, would give us a, and the value of a is 2. So that's also working well. And then if c gets bumped a tiny amount in h by h, then of course a times b is unaffected, and now c becomes slightly bit higher what does that do to the function? It makes it slightly bit higher because we're simply adding c. And it makes it slightly bit higher by the exact same amount that we added to c. And so that tells you that the slope is 1. That will be the rate at which d will increase as we scale c. Okay, so we now have some intuitive sense of what this derivative is telling you about the function, and we'd like to move to neural networks. Now, as I mentioned, neural networks will be pretty massive expressions, mathematical expressions. So we need some data structures that maintain these expressions, and that's what we're going to start to build out now. So we're going to build out this value object that I showed you in the README page of Micrograd. So let me copy paste a skeleton of the first very simple value object. So class value takes a single scalar value that it wraps and keeps track of, and that's it. So we can, for example, do value of 2.0, and then we can we can look at its content. And Python will internally use the repr function to return this string. Whoops, like that. So this is a value object with data equals 2 that we're creating here. Now what we'd like to do is we'd like to be able to have not just like 2 values, but we'd like to do a plus b, right? We'd like to add them. So currently you would get an error because Python doesn't know how to add 2 value objects. So we have to tell it. So here's addition. So you have to basically use these special double underscore methods in Python to define these operators for these objects. So if we call if we use this plus operator, Python will internally call a dot add of b. That's what will happen internally. And so b will be the other, and self will be a. And so we see that what we're going to return is a new value object, and it's just it's going to be wrapping the plus of their data. But remember now, because data is the actual numbered Python number, so this operator here is just the typical floating point plus addition now. It's not an addition of value objects, and will return a new value. So now a plus b should work, and it should print value of -1, because that's 2 plus minus 3. There we go. Okay, let's now implement multiply, just so we can recreate this expression here. So cryptic, we actually are, the object will be dot add of c. And so let's see if that worked. Yep, so that worked well. That gave us 4, which is what we expect from before. And I believe we can just call them manually as well. There we go. So, yeah. Okay, so now what we are missing is the connective tissue of this expression. As I mentioned, we want to keep these expression graphs, so we need to know and keep pointers about what values produce what other values. So here, for example, we are going to introduce a new variable, which we'll call children, and by default it will be an empty tuple. And then we're actually going to keep a slightly different variable in the class, which we'll call underscore prev, which will be this. set of children. This is how I did it in the original micrograd, looking at my code here. I can't remember exactly the reason. I believe it was efficiency, but this underscore children will be a tuple for convenience, but then when we actually maintain it in the class, it will be just this set, I believe for efficiency. So now when we are creating a value like this with a constructor, children will be empty and prev will be the empty set. But when we're creating a value through addition or multiplication, we're going to feed in the children of this value, which in this case is self and other. So those are the children here.
Hi everyone, hope you're well. And next.
In the last chapter, you and I started to step through the internal workings of a transformer. This is one of the key pieces of technology inside large language models and a lot of other tools in the modern wave of AI. It first hit the scene in a now famous 2017 paper called Attention is All You Need, and in this chapter, you and I will dig into what this attention mechanism is, visualizing how it processes data. As a quick recap, here's the important context I want you to have in mind. The goal of the model that you and I are studying is to take in a piece of text and predict what word comes next. The input text is broken up into little pieces that we call tokens, and these are very often words or pieces of words, but just to make the examples in this video easier for you and me to think about, let's simplify by pretending that tokens are always just words. The first step in a transformer is to associate each token with a high-dimensional vector, what we call its embedding. Now, the most important idea I want you to have in mind is how directions in this high-dimensional space of all possible embeddings can correspond with semantic meaning. In the last chapter, we saw an example for how direction can correspond to gender, in the sense that adding a certain step in this space can take you from the embedding of a masculine noun to the embedding of the corresponding feminine noun. That's just one example. You could imagine how many other directions in this high-dimensional space could correspond to numerous other aspects of a word's meaning. The aim of a transformer is to progressively adjust these embeddings so that they don't merely encode an individual word, but instead they bake in some much richer contextual meaning. I should say up front that a lot of people find the attention mechanism, this key piece in a transformer, very confusing, so don't worry if it takes some time for things to sink in. I think that before we dive into the computational details and all the matrix multiplications, it's worth thinking about a couple examples for the kind of behavior that we want attention to enable. Consider the phrases American true mole, 1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these based on the context. But after the first step of a transformer, the one that breaks up the text and associates each token with a vector, the vector that's associated with mole would be the same in all three of these cases, because this initial token embedding is effectively a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic embedding to move it to one of these more specific directions as a function of the context. To take another example, consider the embedding of the word tower. This is presumably some very generic, non-specific direction in the space associated with lots of other large, tall nouns. If this word was immediately preceded by Eiffel, you could imagine wanting the mechanism to update this vector so that it points in a direction that more specifically encodes the Eiffel Tower, maybe correlated with vectors associated with Paris and France and things made of steel. If it was also preceded by the word miniature, then the vector should be updated even further so that it no longer correlates with large, tall things. More generally than just refining the meaning of a word, the attention block allows the model to move information encoded in one embedding to that of another, potentially ones that are quite far away, and potentially with information that's much richer than just a single word. What we saw in the last chapter was how after all of the vectors flow through the network, including many different attention blocks, the computation that you perform to produce a prediction of the next token is entirely a function of the last vector in the sequence. So imagine, for example, that the text you input is most of an entire mystery novel, all the way up to a point near the end, which reads, "Therefore the murderer was." If the model is going to accurately predict the next word, that final vector in the sequence, which began its life simply embedding the word was, will have to have been updated by all of the attention blocks to represent much more than any individual word, somehow encoding all of the information from the full context window that's relevant to predicting the next word. To step through the computations though, let's take a much simpler example. Imagine that the input includes the phrase, "A fluffy blue creature roamed the verdant forest." And for the moment, suppose that the only type of update that we care about is having the adjectives adjust the meanings of their corresponding nouns. What I'm about to describe is what we would call a single head of attention, and later we will see how the attention block consists of many different heads run in parallel. Again, the initial embedding for each word is some high-dimensional vector that only encodes the meaning of that particular word with no context. Actually, that's not quite true. They also encode the position of the word. There's a lot more to say about the specific way the positions are encoded, but right now all you need to know is that the entries of this vector are enough to tell you both what the word is and where it exists in the context. Let's go ahead and denote these embeddings with the letter E. The goal is to have a series of computations produce a new refined set of embeddings where, for example, those corresponding to the nouns have ingested the meaning from their corresponding adjectives. And playing the deep learning game, we want most of the computations involved to look like matrix vector products, where the matrices are full of tunable weights, things that the model will learn based on data. To be clear, I'm making up this example of adjectives updating nouns just to illustrate the type of behavior that you could imagine an attention head doing. As with so much deep learning, the true behavior is much harder to parse because it's based on tweaking and tuning a huge number of parameters to minimize some cost function. It's just that as we step through all of the different matrices filled with parameters that are involved in this process, I think it's really helpful to have an imagined example of something that it could be doing to help keep it all more concrete. For the first step of this process, you might imagine each noun, like creature, asking the question, "Hey, are there any adjectives sitting in front of me?" And for the words fluffy and blue to each be able to answer, "Yeah, I'm an adjective and I'm in that position." That question is somehow encoded as yet another vector, another list of numbers, which we call the query for this word. This query vector, though, has a much smaller dimension than the embedding vector, say 128. Computing this query looks like taking a certain matrix, which I'll label WQ, and multiplying it by the embedding. Compressing things a bit, let's write that query vector as Q. And then anytime you see me put a matrix next to an arrow like this one, it's meant to represent that multiplying this matrix by the vector at the arrow's start gives you the vector at the arrow's end. In this case, you multiply this matrix by all of the embeddings in the context, producing one query vector for each token. The entries of this matrix are parameters of the model, which means the true behavior is learned from data, and in practice, what this matrix does in a particular attention head is challenging to parse. But for our sake, imagining an example that we might hope that it would learn, we'll suppose that this query matrix maps the embeddings of nouns to certain directions in this smaller query space that somehow encodes the notion of looking for adjectives in preceding positions. As to what it does to other embeddings, who knows? Maybe it simultaneously tries to accomplish some other goal with those. Right now, we're laser focused on the nouns. At the same time, associated with this is a second matrix called the key matrix, which you also multiply by every one of the embeddings. This produces a second sequence of vectors that we call the keys. Conceptually, you want to think of the keys as potentially answering the queries. This key matrix is also full of tunable parameters, and just like the query matrix, it maps the embedding vectors to that same smaller dimensional space. You think of the keys as matching the queries whenever they closely align with each other. In our example, you would imagine that the key matrix maps the adjectives, like fluffy and blue, to vectors that are closely aligned with the query produced by the word creature. To measure how well each key matches each query, you compute a dot product between each possible key-query pair. I like to visualize a grid full of a bunch of dots, where the bigger dots correspond to the larger dot products, the places where the keys and queries align. For our adjective noun example, that would look a little more like this, where if the keys produced by fluffy and blue really do align closely with the query produced by creature, then the dot products in these two spots would be some large positive numbers. In the lingo, machine learning people would say that this means the embeddings of fluffy and blue attend to the embedding of creature. By contrast, the dot product between the key for some other word, like the, and the query for creature, would be some small or negative value that reflects that these are unrelated to each other. So we have this grid of values that can be any real number from negative infinity to infinity, giving us a score for how relevant each word is to updating the meaning of every other word. The way we're about to use these scores is to take a certain weighted sum along each column, weighted by the relevance. So instead of having values range from negative infinity to infinity, what we want is for the numbers in these columns to be between 0 and 1, and for each column to add up to 1, as if they were a probability distribution. If you're coming in from the last chapter, you know what we need to do then. We compute a softmax along each one of these columns to normalize the values. In our picture, after you apply softmax to all of the columns, we'll fill in the grid with these normalized values. At this point, you're safe to think about each column as giving weights according to how relevant the word on the left is to the corresponding value at the top. We call this grid an attention pattern. Now, if you look at the original transformer paper, there's a really compact way that they write this all down. Here, the variables q and k represent the full arrays of query and key vectors, respectively, those little vectors you get by multiplying the embeddings by the query and the key matrices. This expression up in the numerator is a really compact way to represent the grid of all possible dot products between pairs of keys and queries. A small technical detail that I didn't mention is that for numerical stability, it happens to be helpful to divide all of these values by the square root of the dimension in that key query space. Then this softmax that's wrapped around the full expression is meant to be understood to apply column by column. As to that v term, we'll talk about it in just a second. Before that, there's one other technical detail that so far I've skipped. During the training process, when you run this model on a given text example, and all of the weights are slightly adjusted and tuned to either reward or punish it based on how high a probability it assigns to the true next word in the passage, it turns out to make the whole training process a lot more efficient if you simultaneously have it predict every possible next token following each initial subsequence of tokens in this passage. For example, with the phrase that we've been focusing on, it might also be predicting what words follow creature and what words follow the. This is really nice because it means what would otherwise be a single training example effectively acts as many. For the purposes of our attention pattern, it means that you never want to allow later words to influence earlier words, since otherwise they could kind of give away the answer for what comes next. What this means is that we want all of these spots here, the ones representing later tokens influencing earlier ones, to somehow be forced to be 0. The simplest thing you might think to do is to set them equal to 0, but if you did that, the columns wouldn't add up to 1 anymore. They wouldn't be normalized. So instead, a common way to do this is that before applying softmax, you set all of those entries to be negative infinity. If you do that, then after applying softmax, all of those get turned into 0, but the columns stay normalized. This process is called masking. There are versions of attention where you don't apply it, but in our GPT example, even though this is more relevant during the training phase than it would be, say, running it as a chatbot or something like that, you do always apply this masking to prevent later tokens from influencing earlier ones. Another fact that's worth reflecting on about this attention pattern is how its size is equal to the square of the context size. So this is why context size can be a really huge bottleneck for large language models, and scaling it up is non-trivial. As you might imagine, motivated by a desire for bigger and bigger context windows, recent years have seen some variations to the attention mechanism aimed at making context more scalable, but right here, you and I are staying focused on the basics. Okay, great. Computing this pattern lets the model deduce which words are relevant to which other words. Now, you need to actually update the embeddings, allowing words to pass information to whichever other words they're relevant to. For example, you want the embedding of fluffy to somehow cause a change to creature that moves it to a different part of this 12,000 dimensional embedding space that more specifically encodes a fluffy creature. What I'm going to do here is first show you the most straightforward way that you can do this, though there's a slight way that this gets modified in the context of multi-headed attention. This most straightforward way would be to use a third matrix, what we call the value matrix, which you multiply by the embedding of that first word, for example, fluffy. The result of this is what you would call a value vector, and this is something that you add to the embedding of the second word, in this case something you add to the embedding of creature. So this value vector lives in the same very high dimensional space as the embeddings. When you multiply this value matrix by the embedding of a word, you might think of it as saying, if this word is relevant to adjusting the meaning of something else, what exactly should be added to the embedding of that something else in order to reflect this? Looking back in our diagram, let's set aside all the keys and the queries, since after you compute the attention pattern, you're done with those. Then you're going to take this value matrix and multiply it by every one of those embeddings to produce a sequence of value vectors. You might think of these value vectors as being kind of associated with the corresponding keys. For each column in this diagram, you multiply each of the value vectors by the corresponding weight in that column. For example, here, under the embedding of creature, you would be adding large proportions of the value vectors for fluffy and blue, while all of the other value vectors get zeroed out, or at least nearly zeroed out. And then finally, the way to actually update the embedding associated with this column, previously encoding some context-free meaning of creature, you add together all of these rescaled values in the column, producing a change that you want to add that I'll label delta E, and then you add that to the original embedding. Hopefully, what results is a more refined vector encoding the more contextually rich meaning, like that of a fluffy blue creature. And of course, you don't just do this to one embedding, you apply the same weighted sum across all of the columns in this picture, producing a sequence of changes. Adding all of those changes to the corresponding embeddings produces a full sequence of more refined embeddings popping out of the attention block. Zooming out, this whole process is what you would describe as a single head of attention. As I've described things so far, this process is parameterized by 3 distinct matrices, all filled with tunable parameters: the key, the query, and the value. I want to take a moment to continue what we started in the last chapter with the scorekeeping, where we count up the total number of model parameters using the numbers from GPT-3. These key and query matrices each have 12,288 columns, matching the embedding dimension, and 128 rows, matching the dimension of that smaller key query space. This gives us an additional 1.5 million or so parameters for each one. If you look at that value matrix by contrast, the way I've described things so far would suggest that it's a square matrix that has 12,288 columns and 12,288 rows, since both its inputs and its outputs live in this very large embedding space. If true, that would mean about 150 million added parameters. And to be clear, you could do that. You could devote orders of magnitude more parameters to the value map than to the key and query. But in practice, it is much more efficient if instead you make it so that the number of parameters devoted to this value map is the same as the number devoted to the key and the query. This is especially relevant in the setting of running multiple attention heads in parallel. The way this looks is that the value map is factored as a product of two smaller matrices. Conceptually, I would still encourage you to think about the overall linear map, one with inputs and outputs both in this larger embedding space, for example taking the embedding of blue to this blueness direction that you would add to nouns. It's just that it's broken up into two separate steps. The first matrix on the right here has a smaller number of rows, typically the same size as the key query space. What this means is you can think of it as mapping the large embedding vectors down to a much smaller space. This is not the conventional naming, but I'm going to call this the value down matrix. The second matrix maps from this smaller space back up to the embedding space, producing the vectors that you use to make the actual updates. I'm going to call this one the value up matrix, which again is not conventional. The way that you would see this written in most papers looks a little different. I'll talk about it in a minute. In my opinion, it tends to make things a little more conceptually confusing. To throw in linear algebra jargon here, what we're basically doing is constraining the overall value map to be a low-rank transformation. Turning back to the parameter count, all four of these matrices have the same size, and adding them all up, we get
How did a single paper, attention is all you need, reshape the entire AI landscape? In this video, we will unpack the transformer architecture. We will see how it works, what makes it so powerful, and why it replaced almost every older neural network design. Before diving in, let's take a quick step back. The goal of machine learning is to learn a mapping from inputs to outputs. For example, in predicting house prices, an ML model maps features like the number of bedrooms, location, and zip code to a price. In a spam detection, an ML model maps a sequence of words or characters to a binary output, a spam or not a spam. An effective way to learn this mapping is through neural networks. A neural network is just a sequence of layers, each transforming an input to an output through its parameters. For example, a linear layer applies a linear transformation to its input. By stacking several layers, we form a long chain of mathematical operations that transform inputs into outputs. The parameters of these layers are updated during training to learn an accurate mapping from the input space to the output space of the task at hand. But for sequential tasks, such as sentiment analysis, things get tricky. If each token in a sequence, say each word in a sentence, is processed and transformed independently, the model loses all sense of context.
Today's video is sponsored by Clerk, the complete authentication and user management platform for developers. Forget writing thousands of lines of boilerplate. Clerk gives you customizable UI components and powerful APIs that work with any framework. As sign-in, user profiles, work management, even billing, in minutes, not weeks. Start reinventing the wheel.
Transform each other directly. You can think of attention as a communication layer built inside the network. Each token looks at all others and decides which ones are important for better learning the mapping for the task at hand. This mechanism allows the model to capture context efficiently, whether a keyword appeared 2 steps away or 200. Now let's unpack the architecture. The transformer includes an encoder and a decoder. Both are made of stacked blocks. Each block has two key layers, an attention layer and a feed-forward or MLP layer. The attention layer is where all the tokens interact, while in the MLP layer, each token privately refines its representation. Let's walk through a concrete example. Suppose the input sentence, Jake learned AI even though it was difficult. In the attention layer, the word it looks at all other words to figure out what it refers to. It learns that Jake is the most relevant token. Other tokens also update themselves by looking at each other and exchanging information with each other. The outputs are updated representations for each token, borrowing information from tokens that are most relevant to them. Then, in the MLP layer, the token it refines that understanding internally and adjusts its own representation. This combination of communication in attention and then individual refinement through the MLP layer is what helps the transformer build contextual understanding. Other details, such as residual connections and layer normalization, are there just to keep training stable. Now, let's walk through how inputs flow through the transformer. First, a tokenizer splits text into smaller units called tokens. Then the input tokens are embedded. That is, transformed into numerical vectors intended to capture their semantic meaning after training. Now, transformer has no sense of order by default. So we add positional information to embeddings to introduce a sense of order among tokens. These are special patterns added to embeddings to tell the model where each token is in the sequence. Without this, Jake learned AI could look the same as AI learned Jake. At each step, attention mixes information across tokens, and the NLP polishes each token individually. At the end, we still have a sequence of vectors, now reach context-aware representations. Depending on the